Mike, you want that attendance sent to you tonight with the tonight's included on there?
I appreciate it if you could.
Okay, as soon as I take it and I catch it up for today, I will email it.
Perfect.
First thing is you have homework for me. Rob, make sure they got a name on them. You folks make sure you get a name on it for me.
You mind if I send it to you in an email?
No, that's
I didn't
cool.
know the printer wasn't working.
No, that's you got it in a Word document?
Yeah.
Yeah, just attach it to an email.
Barbara had her stuff in her hands. I didn't want to ask her.
Yeah, cool. Attach it to an email, like put your name in the title.
All
The second thing is since we had whatever Tuesday was, I had sent you an email and asked you to watch like a couple recordings. I want to talk a little bit about that stuff tonight, but not as much detail as like you need to go watch those recordings. The reason for two is because I don't know what's off, but it took both of them to cover what we were going to cover on Tuesday. So go watch those, right? You know, where they're at, they're in D2L. You know, you get in your site. So when we get in here, there's a box that all of you have that is this Video Archives 2019. Notice the password's 1530. If you hit this little, go to that link. And then the safe thing is go to the bottom, and then you can find all of mine. Right, there's 7 of them there, you know, the one starting tonight. And then I asked you to watch the September 11th and 13th from last semester to make up for Tuesday, please. Right, because I'm not going to go in as much detail as I obviously would do there. So I would appreciate if you would do that over the weekend if you didn't already do it. And then I've got homework 2 for Tuesday. And Tuesday's the 5th. So these problems are out of chapter 2. I've got 2.3, 2.7, and in 2.7, you know, I always tell you when you need to make something in Minitab, and what you need there is the Minitab part you need here is box plot. I would appreciate it there. It's going to ask you, I think, for the 5-number summary. You do it by hand. I know there's a bunch of pieces of data, but they're already in order for you. And that's always the hardest part. All right? And then 2.9. I must not need any Minitab there. And then I picked some of the multiple choice ones. Remember, I underlined those for you. All I need there is your answer. And then there's this 2.31. And what you're going to need there out of Minitab is a histogram. And I don't want to give the answer to the problem away. So when I say summary, you've got 1 or 2 choices for how to measure the center and spread. You either got the 5-number summary, right? Remember the median, the first, third quartile, the minimum, the maximum. Or you got the mean and standard deviation. Watch the recording, you'll hear me talk about the standard deviation. Right? We talked about the mean already. And in the recording, I show you how to get Minitab to do that for you, whichever one you want. Actually, it gives them all to you. So that's why I'm writing summary there. You can get Minitab to do it for you there. Okay? And then there's problem 2.46. And what you need out of there is, obviously you got to answer whatever they're talking with you about, but you need something called side-by-side box plots. So when you watch the recording from whichever one it is, you'll see me make a box plot. You'll see me go to one of these problems around. Now, I might have done 2.46 in class last semester. I don't know, right? But you'll see more than one box plot on the same graph. I don't want to talk too much about that because I want you to go back and I want you to watch those recordings. Right? So that's for Tuesday. It'll all work exactly the same as the first homework did. Now, my thought is this about, I'm telling you to go back and watch this and watch that and all this. I was going to come to this homework here, and I just want to show you, just to make sure that we all see how to make a box plot and that kind of stuff. So I've got Minitab up for you. And I'm going to go and I'm going to go to open, right, because I got Minitab up and running. I think this might be useful for some of us. We have Minitab up and running. And so when I get here, a lot of times when I come in, it looks like this, right? And so I'm going to click on this PC, and then I'm always looking for capital C, your C drive on whatever my computer name is. You know, at home, mine's like, I can't remember what mine is, right? But here, my computer is this KUC 232 ITV, so I'm going to double click that. And then I come over here and I'm going to look for users. Now, if you click on some C and you don't see all this shit on the right hand side, you clicked on the wrong C, I guarantee you. Like when you don't see any, nothing like this. And so I'm going to double click users, and then there's more crap here that's going to be on your computer. I'm looking for my username at ETSU. Remember, this is for PCs, right? And then I'm going to click, once I chose my username, that should be the desktop of this computer. So if I double click desktop, you'll notice there's that Minitab folder where I extracted from the zip and all that stuff. And I got it kind of down a couple there, and then there's my chapter 2. Now, the first one I wanted to take a little look at here was, one of the homework problems I gave you was 2.7, right? So remember, just for the sake of things, you see those are like EG021 with the name and EG0202? Those are the examples. I never give you friggin' examples to do for homework because there were examples in the book, right? You're always looking for these EXs. EX means exercise. I know it's screwed up, all right? And so I'm looking for this EX207, 0207, and even when I look in the book and find that problem, and that problem is on page 55, right at the end of the problem, there's a little thing there that looks like some kind of data thing, and they give you the title of the thing you're looking for, and it's called mid-card. All right, that's how you know you've got the right one. And so when I double-click, I click OK, and then so I've got like 200 and some or something crazy number of cars, and what I have is like their miles per gallon, right? I got 186 of them, all right? And I just wanted to make a box plot of this data for you, okay? Because we talked a little bit about the 5-number summary last Thursday. Remember, it's always in this order. Minimum, first quartile, median, third quartile, maximum. So the way you make a box plot is you go to graph. Down here, on the third little chunk there's a box plot. Right? Now, I only want a simple one. You notice I got choices. I got like a simple one. I got with groups. In other words, if I had more than one categorical variable measured on 2 or more groups, I would use that one. But here I've got one group, and I've got one quantitative variable. So I'm going to click that. And then it wants to know, hopefully, window pops up, where's the variable you're trying to graph? In other words, where's your quantitative variable? And it's in column 1. And we'll click OK. Right, so that's what's called a box plot. Now, in your box plot, just because I didn't talk about it last Thursday, that value right there, that's your minimum. That's the first quartile, that's the median, that's the third. The box plot shows you the 5-number summary, right? And it's actually always in that order, and I always make them so they're standing up like that. And it always goes minimum, first quartile, median, third quartile, and maximum. Yes? Okay. Well, the other thing that, if you watched, you're going to see Minitab's trying to tell you something. You see those little ones that are marked with an asterisk? They're trying to tell you those are outliers. Because when you watch the recording, you're going to be something called the 1.5 times IQR rule. If you're far enough away from the third quartile or far enough above the third or far enough below the first, Minitab's doing the work for us. That's the deal with that, all right? So don't freak out that, in the book you don't ever see any of these ones with the asterisks. Minitab's keeping track of these possible outliers based off of that rule that is in our book, all right? Now, the other thing I want to show you is, okay, so that's the box plot. I'm going to kind of slide it over here. And then if we'll go to stat, basic statistics, because all these means and standard deviations and 5-number summary, these are basic statistics, right? Basic things we calculated. And we want to display descriptive statistics. In other words, we want measures for center and spread. That's what the 5-number summary and the mean and standard deviation are. So if I go there, I click OK, and just like every other thing in Minitab, another window pops up and wants to know, where's your data? Well, my data is in miles per gallon. I'm going to click OK. Now, just for the sake of things, you see that? That's the 5 numbers on it. Yep. Minimum, first quartile, median, third quartile, maximum. I need to change this just a hair here. This is your X bar mean you've talked about. You know the mean where we add them all up and divide by the total number. And then on your reporting, you're going to see that's the notation we use for the standard deviation. That's that little S here that shows up at the end of chapter 2. Why did I change colors? Because the mean and standard deviation always stay in this hand, and the 5 number summary always stays in this hand. Right? So it does it all for you. And then while we're here, you see that? That's how many observations you have. Remember I showed you there was 186 at the bottom? We're not normally concerned about capital N star. That would be the number of blank ones. In case some crazy shit like somebody left something out, when you're looking at data like that. Don't worry about that yet. That's like chapter 18 or something. All right? So it'll do that for you. Now, if you'll notice, if I come back over here, and I'm going to clear this ink again, just like every other time I've been in Minitab, like if I put my cursor there, it's giving me the first, the median, the third. Well, it's matching up with what I got over here, right? Just another way to see the same thing. Okay. Even if I hold it on one of these guys, it'll tell you that value was 58. We know it's an outlier. If I come down here and maybe it won't show me that bottom. Oh, no, it does. See the whiskers? I'm going to put it here. You see where it says whiskers? 11 is the minimum. 39 is not quite the maximum. 39, Minitab does a weird thing. It doesn't go all the way up to the maximum if these guys are outliers. It stops at the ones that are not outliers, and it calls that the whiskers. It'll show it to you. All right? Look. I just want to make sure something I got at least everything here. 231 is a histogram. You already know how to make a histogram from chapter 1, right? And then the summary, depending on what you picked, I showed you how to get the 5 number summary and the mean standard deviation all together. The only other one I wanted to look at was this 246, where I get this idea of side-by-side box plots. How do I make that? So I need to find this problem, 2.46. So look, once you're in here and you stayed in there, then you don't have to go through that whole sequence of stuff I did. I'm looking for 0246, the one titled Odors. When I look in the book, it's titled Odors. Now I want you to notice how this one's laid out. You see this first column? Look, what 2.46 is this? They've measured how much people spent, depending the odor that was in the restaurant, I think is what it is. One night they had a lavender odor, one night they had a lemon odor, and one night they had a no odor. And they wanted to know if there was any, did we say anything about how much people spend according to the odor that was in the restaurant? So the deal is this. You see that first column? That's a categorical variable, right? The type of odor that's in the restaurant. No odor, lemon odor, lavender odor, right? You see the second column? That's your quantitative variable. How many? I'm thinking that's the number of euros. It might have been the percentage tip or something like that. Okay? She's shaking her head when I said lavender odor. Don't you know lavender odor is like a relaxing and supposed to make everybody happy? Okay. I know I haven't said much about the box plot, but this is the perfect spot for side-by-side box plots. You know how I made one box plot with the miles per gallon? You're going to have 3. You're going to have one for lavender, lemon, and no odor. Actually, the best use of the box plots are side-by-side, where you have a single quantitative variable measured on 2 or more groups, and you want to compare the variable's distribution for the different groups. Watch the recording. You'll hear me say that about 8 times. Box plot with groups this time, right? Because I got groups. Okay. Where I want to graph, where's my quantitative variable, and then where's my categorical variable? Where are my groups? Well, they've got it nice for us. It's all the odors, right? Notice, don't freak out that like there's nobody down here or whatever. That just means the minimum and the first quartiles are the exact same values. right? Like if I put there. The whiskers are 18 and a half and 25 and 25.9. There's no outliers there. Notice the first quartile is 18 and a half, so you're not going to see any line down there to the minimum because it is the same as the first quartile. That's fine. Look here, this one's even more screwed up. Hell, the median and the third quartile are the exact same value. Well, okay. Okay? And then so, you'll notice there's a box plot for lavender, lemon, node. Yep. What's that? That's the amount of euros or like the percentage tip they get. What I want to know is looking at this. So I've got this same quantitative variable measured on 3 different nights, 3 different odors. Did one odor make people spend more or tip more? Do you see how the lavender one went up here, like the main part, and the other 2 are down here? Do people spend more on the average with the lavender odor, or they tip more with the lavender odor? And the answer is, yeah, it's up here. What do you think about the no odor and the lemon odor? If you was going to waste your money and put a lemon odor in a restaurant, don't. Just leave no odor. It's about the same, right? This one's up here. These 2 are here. Oh, they spent more with this one. I'm comparing them. A couple of these have an outlier, right? The lemon has a high outlier. The no odor has a high outlier. I don't see any outliers with the lavender. I'm comparing the distribution of, if that's either euros spent or the percent tip in euros, I'm comparing the 3. That's the best use of a box plot. It's side by side. Okay? So I think I've made everything you need. And if you watch the recordings, I've made everything you need for the homework. Now it's just like interpret and say what you need to do. Okay? I would like to step over here in chapter 3 a little bit. I'm going to hit the high points at the beginning of this one because I know that the recording goes all the way through to page 79 here. And actually, that's the really straightforward part of chapter 3. And chapter 3, the title of it is something called the normal distribution. Now look, me and you hopefully already know when somebody talks about a distribution, what are they talking about? They're talking about 2 things, right? What values your variable can take and how often that the variable takes those values. That's what a distribution is. Yep. But there's something special here. There's these really nice, something called normal. Okay? Now, when I say I'm going to hit the high points here, here's what we want to do. We already know that when we're in chapters 1 and 2, hell, they went right together. And look, let's be clear here. We're looking at a single quantitative variable here. That's what we're looking at. No categorical. We just got a single quantitative variable we're interested in. So in chapters 1 and 2, we learned how to plot your data with a quantitative variable. It's either a histogram or a stem plot. We're going to forget about a stem plot for a little bit. We're going to talk about a histogram. In chapter 2, we learned how to calculate measures of center and spread, mean and standard deviation, 5-number summary. And then there's a new step. All right? And I'm going to give it like this. I'm going to call this number 4. Because I see all that, the first 3 things I said there, that's 1, 2, and 3. There's no need for me to write that down. That's chapters 1 and 2. And the overall pattern, you know the shape, is so regular. How about nice? Very defined when you look at it in the histogram. We can describe it by a smooth curve. So in other words, I can give this to you with a couple different thoughts. The first thought is when I look at the histogram, the pattern's so nice, it's so regular, that I can approximate what you're seeing in your histogram by drawing in a nice smooth curve and trading in the histogram for this smooth curve we want to look at. Another way to think about it is like this, and I don't want to go into too much detail with this little thought, but you realize every time we made a histogram, we had some collection of data, right? You know, you had like 15 individuals, maybe 50, 25, or whatever. Now you understand, and the one I have in my mind is this. We had talked about 15 North Carolina workers and their travel time to work, right? And the book made a point to mention that it was 15 randomly selected North Carolina workers, and we measured their travel time to work. Do you think there's more than 15 North Carolina workers that we could measure their travel time to work on? Oh, there'd be millions. So the histogram is representing the 15. The smooth curve is representing all of them. I wanted to give you both thoughts, right? The histogram looks so nice. Shit, I can draw on a smooth curve. Nobody's going to make me draw on the smooth curve, but I could. Or the histogram's really dealing with the data where the individuals came from, and the smooth curve is dealing with all the individuals that we could have talked to. So here's what I got in my mind, okay, is this. You're going to see, I'm going to do away with your y-axis now because I don't care about it. I'm not going to be worried about heights of bars and all that stuff. So I still have my x-axis like I normally do. The variable is on your x-axis. And let's say I had, what's the shape of that guy? I know all the homework problems I gave you, none of them was roughly symmetric. It was either some kind of skewness or something, right? That's roughly symmetric, yes? Is that pattern very regular? Remember, that's single peak, unimodal, very symmetric. Can I draw on a smooth curve? There's your smooth curve. Now, one of the homework problems I had asked you for, you just turned in, was the one about was it the girls eating fruit? Something like that? One of the questions asked, you know, how many ate 6 or more, and one of the other ones maybe asked what was the percentage that ate less than 2, or it was the other way around, right? And what was we doing? Remember, we looked at the heights of the bars, that told you how many. And then to find the percentage, we took how many divided by the total number. So in a sense, the bars represent a proportion of outcomes, right? Whatever bars you pick out there. Yep. Well, I want to do the same kind of thing with the smooth curve. Because if you look at it, and if I could just wipe out that histogram, the smooth curve is a really good approximation. It's the idealized description of what you're seeing in your histogram. So what I'm going to be interested in is this. Long story short, if I had a nice smooth curve, and remember, down here is the x-axis. This is your variable down here. Right? The variable is down here, whatever your quantitative variable is. And so I'm going to be interested in some value of x, some value of your variable. And I'm going to be interested in the area. Right? Because just like back here, if I started marking off these, do those bars represent some proportion of observations in the data in the histogram? And the answer is, yeah. Well, the approximation is so good, I could just as well have shaded the underneath the curve as I did the bars, right? In other words, I want that area to represent area represents a proportion of observations. Now, I haven't given you the magic word here for this curve. I keep talking smooth curve. I drew that one in there because it was a really good approximation, idealized description of the nice histogram I had on the previous page. I want that area to represent a proportion of outcomes or a proportion of observations, just like the heights of the bars represent some proportion of observations. Now, here's the thing. We don't care just about any smooth curve. We're interested in something called a density curve. All my smooth curves in this class are density curves. We're interested in something called a density curve. Okay? Now, I'm going to quote this definition here that's on page 77. And it says this. A density curve is a curve. Oh, yes. That's fine. There's two things. Always on or above the horizontal axis, the x-axis. Okay? That's fine. We draw them all like that anyway. 2. This is the big one. Has area exactly 1 underneath it. Now, you may ask, okay, so how do I know that? Well, when I draw you a curve and I tell you it's a density curve, we all just assume that the total area under the curve is 1. We want that area 1 to represent 100% of the observations, or a proportion of 1. I'm going to use 3 words interchangeably here. Area under one of these curves, proportion under these curves, percentage under these curves. Area and the proportion are exactly the same. If I've got the proportion, I can find the percentage by moving the decimal place to the right, if you like, multiplying by 100. Okay? So, if I come here and say, all right, I'm going to draw you a density curve. And I'm going to ask you this dumb question a couple times. That's a density curve. Is it on or above the horizontal axis? And the answer is, yeah. What's the area under it? 1. Why? It's a density curve. That area is supposed to represent area 1, proportion 1, 100% of the observations. All right? Now, I keep drawing it like the only density curves are roughly symmetric or anything like that. That's not quite true. All right? What's the shape here? Roughly symmetric. Okay, let me draw you a different one. I have my heart set on these. Is the reason I keep drawing them to look like that. What about one that looks like this? What would you tell me the shape is? Well, if you closed your eyes, could you see the histogram that was there when I drew the little curve over it? And the answer is, yeah, maybe. What's the shape? I'm going to look at you all for a second to make sure we got the right idea where the hell the tails are going. Right? This is skewed. What's the area under this one? It's a density curve. Can you see what the one that looks like it's skewed to the left? The tail is going out to the left. I'm approximating your nice tail going out to the left there. Okay? If you had looked when you was making any of the histograms for the homework, the histogram, the place there at the front, it'll actually draw in that smooth curve for you and give you the histogram and the smooth curve. That's what I'm doing. Now, it turns out a density curve let's see how we want to put this. How do I want to put this? Has a center and spread. Variability. just like a histogram, right? Just like a distribution has a center and spread variability. A density curve, you're approximating what you're seeing in the histogram, it will also have a center and spread. Well, can we just cut through the crap? And I'm not interested in any bars anymore. I'm interested in areas under this curve, this density curve. And so, let me ask you this. If I draw one that looks like this, what's that shape? That's roughly symmetric, right? Single peak. Where would be the median? Where's the 50-50 area point? Where's half as smaller, half as larger? Right? When I drew you a nice symmetric histogram, where did I tell you the median was? Dead in the middle, right? Now, what about the quartiles? Where should they be? I got to go about the same distance on either side to get 25 and 25, right? So I would say this would be somewhere around your first quartile. Right here would be somewhere around your third quartile. Right, and what I'm talking about is this. If I could draw that line straight up, there would be 50% of the area here, 50% here. If I could draw these lines straight up and look at this area, what would there be? There would be 25%, 25%. Right? And that's what the quartiles do. They divide everything up into quarters. Median divides it up into halves. Now, the median of a density curve is this 50-50 point. All right? You want to think about the mean of a density curve as the balance point. In other words, if we could have that density curve made of some solid material, and wherever I put my little finger and I could balance the density curve, right, that picture on my finger, that's where the mean would be. Now, look, I'm going to tell you something, and I'm not going to change my story. I told you before that when I drew you a histogram, and now I'm drawing you a nice density curve, I told you the relationship, I hope, between the mean and median depending on the shape, right? Remember, the mean always gets pulled further out the tail or towards the outliers. We're ignoring any kind of outliers here, right? We've kind of smoothed all that away, but there are tails. So, where would the median be? About in the middle. Where would the balance point be? Shit, it's about in the middle, right? In other words, what I would expect, if I got like a density curve that's roughly symmetric, I would expect the median and the mean to be close to the middle and be close to each other. Go back and look, I told you the same shit about a histogram last week. Right? Same idea. Now, I'm going to draw skewed to the left this time so that we can get our tail going out to the left. That's skewed left. Everybody agree? What's the area under the curve? I'm sorry, I just can't help myself. Area under there is 1. Why? Because I said it was a density curve. Right? Now, what's the relationship between the mean and the median here? Well, where's the median? Where's like the 50-50 area point? Remember, it's over here a little bit, right? Same with histogram. Where's the mean? The mean gets pulled out the tail, yes? So the mean would be... In other words, when I see a density curve that is skewed to the left, I'm expecting the mean to be smaller than the median. If it's skewed to the right, what am I expecting? I'm expecting the mean to be larger than the median. It's the same story I told you about histograms. And if you forget that shit I just said, you won't forget it when you get to the homework. When they start asking you about, well, you're looking at something and I see it skewed to the right, how does the summaries tell you that? Well, the reason that tells you that is because something's pulled further out. Okay? I'm trying to preach that to you. Now, I'm almost to my punchline here. Anybody curious about, I should say anything, but the dude's got symbols for these, but he's writing the words. Am I just screwed up? Why is he doing it? The density curve is an approximation of what you see in the histogram. The histogram is where the data come from that we actually calculate things by hand, right? So, here's the way I want you to think about this. I'm not so worried about the median and the quartiles, but when we have the data, like in chapters 1 and 2, and you had it in your hand, to calculate the mean, we used X bar. Remember, that was the average. We added them all up, divided by the total number. And for the standard deviation, remember that's measuring spread. And I'm going to do it for you like this, because you are going to go watch about the standard deviation. See, the quartiles measure the spread of the middle 50%. What the standard deviation does, it uses the mean as the center, and it measures the spread this way, about the mean being the center. The larger the standard deviation, the more spread there is this way. The smaller the standard deviation, the smaller the spread is this way. Okay? We use, that's a little s. That's from the data. You had it in your hand. Now, when we're speaking of a density curve, this approximation, this idealized description, this mathematical model of what you're seeing with the histogram, look, I gave you all the math terms I could think of. Mathematical model, idealized description, we're approximating what we're seeing. It'll have a mean also. I can't use X bar because we're approximating what you're seeing with the data in the histogram with the density curve. So what we use is, I told you, I warned you, that's the Greek letter mu. It's kind of a U with long tails on it. Okay? And for the standard deviation, what do we use? We use, that's the small case sigma. Remember, we saw the big one where we were adding things, but that's the lowercase sigma. And how did he make that? I mean, my handwriting is not the best, but to make the mu, I just kind of give you a, look, I've made 3 billion of these in my career, so yeah. And for the sigmas like that, okay? So this tells you who somebody's talking about. If we're giving you these, we're actually talking about the data in the histogram. If we're giving you these, we're actually talking about a density curve. Yes, I don't really care about medians and quartiles and that with the density curve. I'm interested in means and standard deviation. I have a reason for that. All right? Now, we have a favorite collection of density curves. And we're interested in something in the title of the chapter called normal distributions. Right? Turns out they are described by normal density curves. Now, I'm always honest with you. I'm only going to say that word density one time. Normal distributions, or variables that we say have a normal distribution, they are described by normal curves. Yes, every curve mean you talk about now is a density curve. All right? So, what makes a normal curve? Well, there's 3 things. Well, there's 4 things. I'm going to give you 3 up front. 1, they're symmetric. 2, they're single peak, unimodal. 3, they're bell-shaped. In other words, a normal curve looks like the ones I started drawing for you first. Right? It looks like this. Symmetry, single peak, bell-shaped. Aren't you curious about how I draw them halfway decent, like my hand's not shaking and none of that shit, it's like I've drawn 3 billion of them in my career also. Right? What's the area under that one? Can I quit? Anytime I draw a density curve, the area is 1, right? Area is 1. Is that symmetric, single peak, bell shape? Yes, it is. That is a normal curve. Almost. Now, here's the thing. We need a little bit of notation and know what we're looking for to be able to describe a normal curve. All normal curves have the same shape. I just described it for you. I wrote it down for you. We choose a particular normal curve by giving 2 things. I need 2 things to describe a normal curve. I know it's symmetric, single peaked, and bell shaped. They all are, right? By giving its mean mu and standard deviation sigma. The notation is like this. Instead of me having to write out this all the time, the notation is as follows. You give me a big capital N to tell me we're looking at a normal curve that's describing some normal distribution, and then you give me 2 things. You give me its mean, and you give me its standard deviation in that order. So that stops us from writing all the crap. It's just some shorthand notation saying, look, I'm looking at this normal distribution. Here's its mean. Here's its standard deviation. All right? Now, I'm going to move my hands like this for a second. The mean's the locator. So on the x-axis, if this thing is symmetric, then we know the mean's sitting right in the middle, right? So if you change the mean, you're just picking the shit up and moving it wherever, and it's going to be centered if the mean's 10, if the mean's 50, minus 30, whatever the mean is, right? That's where you're going to be centered. It's the locator. So when I think about this, the mean is always sitting dead in the middle. It's the locator. It locates where you are on your x-axis or on your horizontal axis. Everybody okay with that, right? That's the center. Mean is your center. It's your locator. Well, I got somebody else too. Sigma controls the spread. The variability. That's what it controls. Now, here's the thing I'm going to tell you again. In terms of a density curve, let's back up for a second. In chapter 2, what the standard deviation does, the mean's your center, right? And the larger your standard deviation is, right? Because the standard deviation is just a number. The larger it is, the more spread out the observations are. The smaller the standard deviation is, the closer the observations are to the mean in the center. So what does it control here? What's the total area under any one of these normal curves being you draw? Standard deviation controls this. How tall it is, how close things are to the center, or how flat it is. They all got to be symmetric, single peak, and bell shape. So here's my thought. To get a little technical with you, I know I'm looking at a normal curve. Here sits the mean. Okay? Actually, it turns out I can eyeball the standard deviation here. So you see how, and I'm not trying to bring calculus into the story, it looks like you're curved down, and then you curve back up, right? You kind of go back up here. You see that point right there where it looks like we went from going down to back up? Anybody who's had Calc 1 would know that was a point of inflection. If you hadn't had Calc 1, that's okay. It's just there's that point, all right? If I come straight down here to whatever that value is on the x-axis below that point where it kind of changes, the distance from here to here is 1 standard deviation. Now, would I ever give you something like this and say, what's the standard deviation of that like that? No. The reason I'm doing this is this, right? Is you can actually eyeball it. Here's my thought. I'm going to draw you 2 pictures, right? 2 normal curves. I want to draw one here. There's your mean. What's the area under that? Don't answer. And I want to draw you this one. They both have the exact same mean. They're both centered at the same spot. What's the area under both of them? 1 and 1. Which one has a larger standard deviation? The one on the top or the one on the bottom? See that point there? That's sigma. See that point out here? That's sigma. The smaller the standard deviation, the taller your density curve is, and the closer things are to the center. The larger your standard deviation, the smaller the peak, and the more spread out things are about your center. It's just, I'm going to move my hands like this on the sides of that density curve. You start giving me a smaller standard deviation, and I start pushing, the peak has to get taller because the total area's got to stay 1. The standard deviation gets larger, I'm pushing your peak down, and I'm flattening that out. Are they all symmetric, single peaked and bell shaped? And the answer is, yeah, those are all symmetric, single peaked and bell shaped. Now, here's my thought. On the bottom of page 81, a normal distribution. I'm reading the box to you here. I'm not going to write it up. It's there. There's a little box there that says normal distributions. A normal distribution is described by a normal density curve. Here. Any particular normal distribution is completely specified by 2 numbers, by giving its mean, where's its center, where's it located, and its standard deviation, sigma, this. It says the mean of a normal distribution is at the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature. Please just remember, the standard deviation is controlling how tall the peak is or how things are spread out. All right? Now, the reason me and you are so interested in normal distributions, normal curves, it turns out a lot of variables we want to study have a normal distribution, right? They're described by one of these normal curves. I need it for probability, like chapter 11, 12. And then I need it for like the last 6 chapters of the semester. I need these normal curves. Look, these normal curves will disappear for like a few weeks, and then they're going to come back to us, and when they come back, they don't disappear again. All right, so that's the deal. We have a lot to do with them. Now, something called 68, 95, 99.7 rule. All normal distributions satisfy this rule. Actually, it's what makes a normal distribution normal. It's what makes a distribution normal. One is symmetric, single peaked, and bell shaped is they got to satisfy this rule. Now, I can read it to you out of the book, or I can start drawing you pictures. What I would like to do is I'd like to draw you some pictures here, because this rule, I mean, it's written out for you on page 82, no problem. I don't really think writing it out in words or any of that's going to help. Here's my thing. Suppose I have a normal distribution. I'm going to write up in here in the corner, it's normal, it's got a mean mu and a standard deviation sigma. I understand, no numbers. I got that part. All right. We know that the mean is sitting right in the middle. Now, the 68 part of the rule says this. If we go out here to the mean plus 1 standard deviation that way, the mean minus 1 standard deviation that way, what I just did is I want 1 standard deviation on either side of your mean. If I look at this area that I'm going to shade here in red, that's 68%. In other words, 68% of the area is between those 2 values, right? 68% of the observations takes a value between those 2 that's on the x-axis there. What's the 95 part? If I go out here to 2 standard deviations on either side, and I look at this area that I'm going to shade in blue, that's 95% of the area. Anybody know what 99.7 is? That's 3 on either side. All right, so if I come out here and go 3 this way, 3 this way, and I'm going to change the color one more time, and I look at this area here that's in green, that's 99.7%. In other words, almost all the observations are within 3 standard deviations of the mean. Now, like I said, the way this is used a lot of times is that people check to see if things are actually normal to see if this is actually true. You know, our 68% of the observations within 1 standard deviation, 95% within 2, 99.7 within 3. Now, look, I can't leave you with this. Not in this class. I can't leave that. I got to have like a problem here, and I want to look at example 3.2 to show you how one of these works just a little bit here. All right? Because this is not the end of our story. I want to read the problem, and you know, I've read problems for you before, and I always read all the words. I try to get the... Have you figured out that every problem in this class is a word problem? Sorry. Every problem in this class is a word problem, so the hardest part is pulling the information out. It says, figures 3.1 and 3.2 on pages 76 and 77, you can go back and look at that later, shows the distribution of Iowa test vocabulary scores for 7th grade students in Gary, Indiana is close to normal. And you're going, dude, you wrote down that big capital N and you didn't read any further. No, I need to know it's normal. If I want to do anything, I got to know it's normal. It says it's normal, and it says it has a mean of 6.84 and a standard deviation of, there's your mu, there's your sigma. So it turns out those Iowa test of basic skills for those Gary, Indiana students, they follow this normal distribution with this as its center and that is its standard deviation. Now, what does it look like? Right? So it's centered at 6.84, wherever that is on your x-axis. Yep. Now, which one's the book do? Let's do the 99.7 part. The book does 95 again, right? So I want to look at the 99.7%. And when I say this to you, what should you be thinking? 99.7 corresponds to what? It corresponds to, can I do that? 3 sigma? 3 standard deviations. If we were talking about 95, I'd have wrote 2. If I was talking about 68, I'd have went 1, right? So, what does it mean to go 3 on either side of the mean here? Well, you're going to get a point out here. I'm not going to write out the symbols this time. I'm going to write out the calculation. You're going to have 6.84 plus 3 times 1.55. Everybody understand where my numbers are? The mean 6.84, standard deviation is 1.55. And this is going to give me a value of, I don't know, 11.49. You agree with me? Hell, I was cheating. Book's got it there. And then if I go 3 the other way, what does that mean? Okay. Well, if I go 3 to that way, I got here is 2.19, right? So in other words, 3 standard deviations to the left is 2.19. 3 standard deviations to the right is 11.49, right? What do I know about the area under the curve between these two values? It is everybody okay with that? Yeah? So then I got to write this next statement in. What is that really telling me? If I tell you the area under the curve from 3 standard deviations here, 2.19, to 3 standard deviations here, 11.49, if the area is 99.7%, what does that really mean? It means 99 0.7% of the test scores fall between 2.19 and 11.40. Yeah, I know what the area is, right? The areas are, but I'm really reading these values on the x-axis, right? Remember, that area represents proportions or percentages of observations. So if I'm 3 on either side, 99.7% of all the test scores, because that's what we're measuring here, fall between 2.19 and 11.49. We okay with that? Could we have done 95? Then I'd have gave you two values and said, oh yeah, 95% of all the test scores are between these two. Could we have done 68? All right, now I got some dumb questions here before we move on. If I give you this, and here sets your mean, in general, what's this area here? Oh no, you can give me the obvious answer. Tell me I'm an idiot, and that's 50%. I'm good. 50%, right? That side's 50%. What's this side? Yeah, well, that's 50% too, right? Yeah. Okay. Hang on. See, because everybody just this whole 69, 68, 95, 99.7, you get that shit stuck in your head. But you know more than that. What I mean is this. Suppose we go 1 out this way. Suppose we go 1 this way. So when I'm going 1 on either side, we're talking about the 68 part, correct? If I look at this area, how much area is that? Tell me. You know, it's 68. Everybody agree? I'm reading right out of the book. I'm not making any magic. Yep. How much is here? Tell me 34? Thank you. How much is here? How much is underneath the whole thing? Area's 100%. If there's 100% total, and I've got 68, how much is on the outside of that? 100 minus 68, which is 32. There's going to be half here, and there's going to be half here. If there's 16 out there, and there's 16 out here, it's got to be half and half. So you know more than just, okay, 1 standard deviation on either side, there's 68 between them. Right? There's actually 68 between them. There's 16 in this tail, there's 16 in this tail, there's 34 here, there's 34 here. Right? You know way more than just what the rule is. And what little fact am I using on you to find that part that's in green? The total under the curve. I'm going to give it to you in terms of a percentage, right? Proportions 1, percentage is. That's how I know. 100 minus 68 leaves me with 32. Half's got to be here and half's got to be here. This is how I get 16 and 16. Right? So there's more to it than just what meets the eye. Now, before we get to the punchline, because that ain't the punchline. All right? I want to know something. How do summary statistics change? What I'm talking about is this. I'm talking about your mean and standard deviation. That's the data, right? I'm back to the data here. The median, quartiles, max, min, and something called the interquartile range. Do not freak out. I know you're going to watch the recording. The interquartile range is the distance from the first to the third, Q3 minus Q1. And what I want to know is this. If I start adding the same value to all the observations or subtracting or multiplying, how does that change these guys? Here's my question. Let's say we have our first test, and the grades aren't overly good. Nothing personal. Let's say like the average is like 60, and I want to bring it up to 70. How can I do that? If I add 10 to everybody's test score, will that change the average? It'll bring it up by 10, yes? So in other words, what I'm thinking about is if I add or subtract the same number, I'm just picking 10, who actually changes? Is the spread or variability changing, or just the location? This one here is going to get added or subtracted 10. Look, you're picking your histogram up and you're moving it by 10 either way. You're not changing this. Okay? The median, quartiles, maximum, minimum, interquartile range, that spread between the first and the third, that's not changing. See, adding or subtracting changes location. It doesn't change the shape of your histogram or your density curve. Okay, so let's say the test scores were really bad. And so I'm going to, just for the sake of things, I'll multiply them all by 2. I'm not saying they're going to be bad, I just got to have something to talk about. So what happens when I start multiplying all the observations in a data set by 2? Do I change location? Yeah. Do I change this? Yeah, I'm spreading things out. Think about it. If your minimum is 4 and your maximum is 10, now you're at 8 and you're 40, right? We're spreading everything out by 2. Everybody changes. Everybody gets multiplied by 2. And divide is the same way. I'm just going to do multiply. Everybody changes. Because not only are we changing location, you are changing you're doing this to your histogram or your density curve. So adding or subtracting changes location. Anything that's measuring spread or variability, like your standard deviation or your spread in the middle 50%, is not changing. You start multiplying or dividing, not only you're changing location, but you're changing spread or variability. Why do I care about that? Well, it turns out I need to. Okay? And the reason I need to is this. Okay, so this is the punchline. I'm going to put that down. I'm going to look at everybody for a second. And I'm going to just tell you, okay, so everything me and you talked about chapter 3. All right, so somebody's going to say, look, I can approximate this histogram. The pattern's so nice, so regular, just have a curve. We got a density curve, right? They're smooth, I call them a smooth curve. You got a density curve. It's got area it's one or above the horizontal axis. I have a favorite collection of density curves, and they're normal curves, right? You give somebody the mean, you give somebody the standard deviation, then I know what the normal curve is I want to work with. See, here's my question. Those Iowa test scores, I got to get you set up to where I'm headed here. Right, so I got the Iowa test scores we just talked about. I know they follow a normal distribution. Right, that was given to me in the exam. So I know those Iowa test scores, they follow a normal distribution, so I know they're symmetric, single peak and bell shapes. I know their mean is 6.84. I know their standard deviation is 1.55. See, the kind of thing I want to know is, what percentage of scores are less than oh no, I picked that number for a reason. See, because I'll come right back here for a second. All right, I just want to do this. See, if I came over here and I started asking you, what percentage was less than 2.19 or bigger than 11.49, or even if I came here and started asking you about, okay, what percentage is greater than 1 here or 1 there, as long as you fall 1, 2, or 3 away, I can draw you a picture that looks like that because I know, there's 100%, I know about 68, 95, 99.7. Unfortunately, six, it ain't 1 away, it's not 2 away, and it's not 3 away. So you might as well take that 68, 95, 99.7 rule in the paper it's on and just wad it up and throw it in the garbage. We can't answer that question using that. Right? If it fell 1, 2, or 3 away, I could answer all kinds of questions 1, 2, or 3 away because I know what I know from before. You're not 1, 2, or 3 away. Can everybody see that? Because if you take 6.84 minus 1.55, you're way less than 6, right? So it's not 1 away that way. You can't do that like that. Now, can we do one more thing before I show you how we're going to handle this? You see that sentence? I'd like to translate it into sentence. I want the percentage. I use big capital P for percentage, proportion, area. I want the percentage where X, whatever variable we're talking about, and we're talking about Iowa test scores, what does it mean to be less than 6 in symbols? Is that correct? Students in this class always hate when I start translating the English language to symbols, but I got you. That's the percentage where X, the scores, Iowa test scores, are less than 6. Okay? So, here's how we solve this problem. There's something called the standard normal distribution. Now, that's not plural. There's only one standard normal. And it turns out, I just want to use the right words on you. If all normal distributions are the same if we measure a certain way, right? So, all normal distributions are the same if we measure in units of size sigma about the mean So if I was talking about the Iowa test scores, I would be thinking 6 was what? 0.84 points smaller than the mean, right? Because remember, the mean was 6.84. So instead of measuring in terms of whatever units the variable come to you, in terms of test scores as points, let's measure in terms of how many standard deviations an observation is or a value is. Well, don't think that's a weird freaking idea. 68 is 1 away, 95 is 2 away, 99.7 is 3 away, right? We've already done that. Now, this has a language all its own, changing to these units. In other words, measuring in terms of the number of standard deviations a value is from the center is called standardizing. That's the term. We standardize a value. What does the standardized value tell me? It tells me how many standard deviations away a value is from the mean. All right? Well, there's a little formula here. And I'm on page 85. It's called the standardized value. You won't hear that out of my mouth a lot, but I get you started with it. I try to get more to the point. The standardized value is called a z-score. Yes, I put a line through my z so you don't think they're 2's. All right, that's a standardized value. And the formula is z is equal to x minus mu divided by sigma. That is a standardized value. That's going to tell you how many standard deviations away from the mean your observation is, right, or your value is. It'll also tell you the direction. Look, sometimes I like to do this with you. If you look at this part here, just focus in on that. So the x, there's some value of the variable we want to standardize, right? Because we want to find out how many standard deviations away from the mean is. So we're going to take that value, we're going to subtract mu from it. What am I doing? I'm giving you a distance from an observation value to its mean, right? If it's to the left of the mean, that value is negative there. I got circled. If it's bigger than the mean, right, that value is positive. Isn't that just a freaking distance? Yep. Yep. We okay with that? So, that distance might be 3.4. What happens when I do this? How many standard deviations fit in that distance? Oh, is it 2.4, 2.3, 1.7? What is it, right? So the top part's giving you the distance. negative on this side, positive on this side of the mean, and then dividing by the standard deviation. You're just fitting how many standard deviations can you fit in there. You're not going to fit a nice number. All right? That's the standardized value. That's your z-score. Now, I got to write this part down for you. It tells us how many standard deviation sigmas the observation falls away from the mean mu and which direction. And the which direction part is, if it's positive, it's larger. If it's negative, it is smaller. If the z-score comes back positive, it's to the right of the mean. If the z-score comes back negative, it's to the left of the mean. Now, before we get to where the punchline is, example 3.4. Again, I need some kind of normal distribution here. We're going to mess with any of this stuff. And I'm going to read it to you. We're going to pick the information out because I'm going to do this to you on every problem because that's the hard part when you see me. It says, the heights of women aged 20 to 29 in the United States are approximately normal. Sorry, that's habit. And when I write that, you better be seeing me read two more things to you. What the hell is the mean of these women's height and what are they standard deviation? It says the mean is 64.2 and the standard deviation is 2.8. There is your mu. There's your sigma. Now, I didn't make anything up. I'm reading that right out of the problem. Approximately normal, normal, that's all good. We're looking at something that's normal. Here's its mean. Here's the standard deviation. We're looking at heights of what? Women aged 20 to 29 in the United States. Turns out they follow a normal distribution. The mean height of that density curve is 64.2 with a standard deviation of 2.8. Now, the z-score would look like this. Since the variable we're looking at is a height, this would be the only time you see me write in what the variable is. I would subtract off your mean, and I would divide by your standard deviation. I'm plugging it into that formula, right? Here's my mu, here's my sigma, and what it really is this. I always think about whatever the variable is, it's an x. If it's the height of women, it's an Iowa test score minus your mean, divided by your standard deviation. You will get tired of hearing me say it like that. It's a value of the variable minus the mean of your distribution divided by the standard deviation. So what I would like to do is, I would like to standardize, fancy term, a height of, pick a number. I mean, the woman's height's got to be positive, right? Can I pick any number I want here? I don't know. Let's pick, I don't want too tall women. Now, you understand what I just gave you here. This right here is, heights were measured in inches, and I just gave you a particular height. Okay. I want to know, when I say standardized height, I want to know, okay, how many standard deviations away from the mean is 68? So all I got to do is take my little formula, and somebody give me a calculator, plug in 68 for the height, or the value of the variable, subtract off your mean, and divide by your standard deviation. I'm going to be a little picky about how you get your answer here. Not with the freaking calculator. How you give me the answer? What do I get here? 1 point. Anybody? Nobody? What did you get? Okay, so when you give me the z-score, I want 2 decimal places. I want the 10th position and the 1st position, 100th position. What did you get? I have a reason for that. Anytime you see me calculate a z-score, I will give you the 10th position and the 100th position. What I mean is, folks, I'm giving you 2 decimal places always. Like I said, I'll have a reason for that come Tuesday, but I have a definite reason for that. So what this is telling me is that 68 is 1.36 standard deviations greater than the mean, right? Positive. It's 1.36 standard deviations greater than the mean. Let's do one more. Can we standardize a height of, now, the reason I picked 5 feet, how's everything given to me here? Is it given to me in terms of feet or what? Inches. So you can't just plug in 5. What we're really looking at is, right? It's got to be with the units of everything, right? So everything here was actually measured in inches when it's given to me, but some idiot's giving me 5 feet. So I need to be looking up 60 inches. So my z-score is,
1.60.
oh, you're way ahead of me. 60 inches, the value of the variable, minus your mean, divided by your standard deviation, and she's telling me it's minus 1.06. 06?
Well, maybe I did it wrong. Something. 1.60 is better.
Oh, I'm sorry. Minus 1.60?
Mm-hmm.
You sure?
No, we didn't.
Well, no, I'm checking the book and it's telling me I'm not right.
Okay. Whatever the book says.
I don't care if there's a 0 in the hundredth position, right? Minus 1.50. I don't care if there's a 0 there. I always want 2 decimal places. So this is telling me that 60, a height of 60 inches, or if you like, a height of 5 feet is 1.50 standard deviations to the left or smaller. The minus is telling me you're going that way. Everybody okay with that? Can I standardize any height you want? Was there anything special about 60 inches, 5 feet? Was there anything special about 68? Can I pick any height you want? And the answer is, yeah, I can tell you how many standard deviations and which way you are. What do I need to know? I need to know that normal distribution, mean and its standard deviation, and whatever variable you're talking about, I can standardize any value you want with my little formula. All right? Now, again, I'm searching for the right words at this moment because something went on here, and it's actually like a pretty big deal, right? Standardizing, calculating z-score. And, I always give you my hillbilly thoughts on it. Standardizing takes and I'm kind of picky about how the problems are. Our normal distribution, and the reason I say that's a little odd, this is the one given in the problem. I think about it as ours at that moment. Standardized takes our normal distribution to the standard normal distribution, of which there is only one. It's normal. Well, if it's normal, you're supposed to be asking me, dude, you're telling me you're looking at a normal distribution, what's its mean and what's the standard deviation? It's the one centered at 0 that has a standard deviation of 1. And when I say takes our normal distribution to it, what it does is, whatever your mean is, in this case 64.2, it picks the shit up and it moves it where it's centered at 0. The standard deviation was 2.8, and now it makes the standard deviation 1. So not only does it pick it up and move it, but it actually shrinks the standard deviation. Now, I know it's time to go to the house. Here, the one we started with. And then we'll come back and pick up here on Tuesday. Right? So, there's the one I was working with the heights of women aged 20 to 29, right? This guy right here. we standardized just for the sake of things. You know, I did like 60 and we did 68, right? So when I say it takes ours into that one, the standard normal one's sitting down here. How do I know that? I just labeled it as normal standard, centered at 0, standard deviation of 1. Okay? It took that value there to the value minus 1.50. It took that value there to the value of 1.36, and it takes that one there to there. What lives here? Values of your variable live on that one. What lives down here? What lives under the standard normal curve? Z-scores. What lives under the normal curve that's given to you? It's whatever value of the variable you're looking at. How does the green work? How did I transform it? What was the calculation? Right? How did I get from 60 to minus 1.5? How did I get from 68 to 1.36? We calculated, we standardized, right? We calculated the z-score. So it takes the one you have. See, I can't move it here. All I can say is it takes all these values here, and it gives you a value down here. It gives you the z-score that lives under the standard normal. I know, we want to go home. I want to go home too. The catch is, suppose I wanted to know this area. In other words, I would like to know the percentage of young women's heights that are less than 60. I ain't got no shot in hell because it's not 1, 2, or 3 away. But it turns out that and that are equal. And on Tuesday, we have a table that will allow me to look it up under the standard norm. I think there's a takeaway. I'll pull it out. We'll work some more problems. We're definitely not done here. But just, if you're going to work any problems here, think about standardizing. Can I calculate that z-score, and then when we come back on Tuesday, we'll start here, and then we'll do some calculations. I'll pull the table out, show you how to read it. Please remember when you calculate a z-score, always 2 decimal places. Again, I have a reason for that. Be careful going to the house, and we'll see you on Tuesday. Please watch the recording. There was more there than I said.
You could do it.
Thank you.
I had computer crash, and I could not get into my
You can get the computer to work?
mine. So
Uh,
I had to do this on my work, and I could not get into it.
no, you can't. You couldn't?
No,
Oh, it won't let you. Oh, no, you can't get anything outside.
Well, anyway, so I did.
But it lets you use.
I've got Excel.
Yeah.
On my program, so I
But-
did the best I could. to make
No,
it
they're
work.
right. Well, no, I mean, it looks very
I
similar.
mean,
It's just,
it does.
but we'll get that fixed, right?
Yeah, my nephew's going to work on it this weekend.
Because I was thinking, where you work?
Union Path.
Oh, yeah, you're not getting outside. It's not going to let you log in the Gold Lab at work.
No.
No. It's not,
Mm-mm.
it doesn't let you get outside of there at all, does it?
Mm-mm.
Uh-uh.
No, and then on my laptop, I had remote access to my desktop because I'm a manager. And I think